Okay. So I'm going to talk about dependent types also, but I'm going to focus on ghost types and equality reflection. And since I'm talking about dependent types, I have to start with the mandatory vector example. So you already know all about it, but I'm going to give maybe a different solution to what Kenji did. So, well, vector is the same type as you saw before, so a way to have a type-based invariant. And if you want to write the reversal function, like the tail recursive version that uses an accumulator, then you would give it this type, where you have a vector of length n, an accumulator of length m, and then the result is of length n plus m. I spare you the details, but essentially if you write this, then you will end up with a type error because of something very annoying, that you have something of length k plus successor of m, while like say coq would like to have something of length successor of k plus m. And well, if you're like me, you think that they should be the same thing because, well, they are, but they're not definitionally equal, so you get an error. So for now, I'm just going to add some kind of star to assume that it actually works. And then when I erase, if I want to extract this program, or let's say for instance just vectors to start with, in OCaml, then I get something that's almost like lists, except that there is this natural number inside here, which I don't care about. And if natural numbers are unary, then you get some like kind of quadratic blow up for just no reason. And if you just look at how you would extract the ref function, then you get something very stupid where you still carry around all these natural numbers. Actually, you see that the pretty printer knows that one of those is useless because it just uses an underscore, but it's still around. And depending on how you set things up, you might even have some obj.magic here that is also useless. But yeah, so what you would really like to have is just lists, right? Because you have the invariant in the dependent type world, and then you just forget about it. So here it's also, as in the previous talk, obviously the problem is always in the n part, right? So the solution I propose is to mark this index as erased, so it's kind of following the f star way of doing things. In this case, I just use erased nat instead of just nat. This means I have to use hide of 0 and ghost successor, even though like maybe a liberation can do it for me. And then in that case, the erasure would just make sure that at extraction, after extraction, the natural number is gone. Okay, so in that setting, essentially you could see hide as a constructor to some erased inductive type that goes from, that's some kind of boxing that goes from type to a new universe that I call ghost. And then this inductive type would have an eliminator that I call reveal, again following the f star naming conventions. The important part is that you cannot use reveal to produce some relevant value. So what you can do is you can go from erase nat to erase nat. That's how I can define the ghost successor. So essentially, I take this erase natural number, I reveal it and call it x. So x is now a proper natural number. I can apply the successor to it and then hide it again. So this is valid. But if I wanted to write a function from erased bool to bool, then it would have to be the constant function, because there's no way to branch on ghost data. So that's to make sure that I can actually just erase it. It's not going to affect the result of a program. And to make the rev example work, I'm also adding some things that you also have in F star, which is equality reflection, but this time restricted to ghost values. So if I have two propositionally equal ghost values, then I consider them to be definitionally equal. So maybe, and then, yeah, if you assume this, then you can just write the rev example from before, and it should type check, because now the index part of vectors is just up to propositional equality. So if, for instance, you have an SMT solver like an F-star, it's just something that's easy for it. Maybe one thing you could ask is, couldn't it just be propositions, right? After all, you have squash, which plays almost the same role as erased. Instead of going from type, you go to ghost, you go from type to prop. And you have something even better than equality reflection. You just say that every proof is equal to every other proof. So the reason I don't want to just use that is that I want to be able to distinguish the empty vector from the non-empty vector, so that I can type check functions like the head on or the tail function, right? So the important part is that I want to be able to distinguish height of 0 and well, height of 1 or the ghost successor of any natural number. Okay, so the problem is that I cannot do the usual trick where I can build a function that matches on it to determine whether it's a 0 or a successor, because I cannot go into type. So the solution is to introduce some kind of reveal, but that produces a proposition instead of producing some proof. So here is the typing rule. Essentially, if you have some function that goes from A to prop and some erased A, then you can build a prop out of it. And the idea is that if you reveal some hidden value, it's the same as just applying the function directly to this value. It's only a logical equivalence, not a computation rule. And then you just get a discriminator by revealing this natural number and matching on X. Now you're allowed to do it. So you can can either return true or false, and then you have something that's discriminating the two. Okay, so how do we justify such type theory? So we just go and interpret it into another different type theory, which also has ghosts. But instead of using ghost reflection, I'm going to use ghost casts, which essentially are similar, but you record in the term which equality you used to go from P of U to P of V. And this translation is essentially the same as what you would get for going from extensional type theory to intensional type theory, if you know. You translate the derivations, and every time you use the conversion rule, you just use the cast rule instead by inserting some casts. And casts don't get in the way because we have this amazing rule that says that I don't care about casts. So I can ignore them and everything is fine. So actually the proof is even easier than the one from extensional type theory to intensional type theory. Of course, the question now is, how do I justify this one? And this time I can just go to some type theory that we know and love and that we know has nice properties, like Martin-Löf type theory. The idea is to use some form of translation that's akin to parametricity, following the idea of exceptional type theory, sorry. So I would say that the one in the middle is actually interesting on its own. So for now, I'm going to focus on the lower part of this diagram. So how do we go from ghost type theory to Martin-Löf type theory? The idea first is to use some notion of erasure that gets rid of all ghosts and all proofs. So if you have a lambda, a function that takes an argument, then you look at it, is it relevant? If so, then you keep it. But if it's not, if it's a ghost or a proof, you just throw it away. You do the same thing for applications, so if you just have a relevant application, you keep the argument and you recurse, but if you have a proof or a ghost argument, then you just throw it away. And of course, as I was saying, I don't care about casts, so I just throw them away. The difficult part is when you want to translate the eliminator for the empty type. So you have here some proof of false. I mean, in the source, if you have a proof of false, then you have a proof of A for any A, or you have an inhabitant of A for any A. But in the target, there's no way to, we've lost the proof of false because we're just getting rid of all proofs. So what you would like to have is say, yeah, I want to raise an exception, or like you do in OCaml, you just say assert false, because this is an unreachable branch. This is exactly what the X-parser should amount to in a program at the end. And so that's where we use the exceptional type theory approach. So instead, every type is now translated to a new type, but also to a distinguished element of it that we call the exception. So that's all well and good, except that now we have obviously an inconsistent model. So we want to, because every type is now inhabited, so we need to be able to make sure that actually we preserve consistency. So let's look at it on an example. So the Booleans is just the inductive with true and false. You erase it to a new inductive type, which also has this bool empty that corresponds to the exception. And then you also do this parametricity translation to get back an inductive type that qualifies the Booleans that are actually good Booleans, the ones that don't use the exception. Right, so just true and false. So that's how you carve it out. Actually, because we use this kind of parametricity, we have some limitations on large elimination. It's not so bad, but yeah, that's something to keep in mind. And then, because it's parametricity, you also get some free theorems. So the meta property that the functions from erase bool to bool have to be the constant functions, you can just prove them internally. Okay. Not internally, you can prove them by the translation, sorry. And then for vectors, this is where it gets maybe more interesting. Now the erasure actually looks more like lists. Well, list with an exception, but you see that the natural number is gone from the type, in the type and in the data. And then that's the parametricity predicate that keeps track of the size. So here it's maybe mixed within, so you don't actually see it, but essentially you have this thing that says that nil is a good vector if it has length 0, and const is a good vector if it has length successor of n, well, exceptional successor of n. You have more oddities in the paper, so I encourage you to look or not to look, depending on what your plan is. And to conclude, so we have this ghost reflection type theory, an interpretation into ghost type theory, and then into Coq. That was all formalized in Coq. This allows us to get back some results like conservativity and consistency, but also some form of type formal discrimination, so that you know that, for instance, vectors are not the same as Booleans. So they're not nice properties like that. There's more to be done, like handling inductive types in general, not just examples, proving sub-properties like subject reduction determination, decidability when you don't have reflection, and maybe look at the meta theory of F star, especially the ghost effect. A student who's actually defending his master's thesis as I speak, I've been working on that and made good progress, so I'm quite happy. Just so final note, there was some tricks also in the formalization to handle context of varying size, because the erasure removes variables from the context, but parametricity adds more, so some trickery to avoid De Bruijn arithmetic. And I've used the very nice autosubstitute library to handle most of the De Bruijn indices, but I had to deal with the slowness of it, so, and hopefully it should come out as improvement on the tool. So you can check out the formalization, and that's all for me. Thanks.
Hi, I'm Jesper Cox from TU Delft. So you're adding this universe of ghost types to your type theory to make this work. So in Idris 2 and Agda, there's only a modality of erasure, which I think is slightly weaker than having a universe. So I was wondering, would the thing that you're presenting here still work if you only have an erasure modality rather than an erasure universe?
So indeed, that's something I mean, I thought about it, but I don't have any concrete evidence, but at least my hope is that it should work as well. It's just that to build the model, for me, it was easier because just no universe is better than modalities. But yeah, I don't see...
There was no reason that you encountered that it wouldn't work?
No, yeah, I don't see any reason that it has to be this way. It's just one way. And
right. And then it would maybe justify adding some equality reflection for erased things.
Yes, yes, this is something that
Agda or Idris, yeah.
Yeah, it would be awesome if we could make something for Agda. Or,
yeah, would be very cool. Okay,
yeah.
Thanks.
Hi. Max New, University of Michigan. So you showed that it's not the same as prop, right? Because you don't really want it to be a prop.
Yeah.
But in homotopy type theory, the propositional truncation is just like the lowest level, but there's also a set truncation, groupoid truncation higher. And I think based on the rules, because you have equality reflection, it forces everything to be a set. So is it accurate to say that this is kind of like an S set that is a form of set truncation that has better definitional behavior?
So I don't want to make any commitment. I mean, it's indeed interesting. So I mean, you cannot have a reflection just for H sets, because then you get reflections for everything. So maybe indeed it's if you have equality reflection on H sets, then you have everything.
On arbitrary H sets, yeah. But then you have this universe
and this
that's
is
sort
S
of
set, and I guess might be a way to carve out the ones that work nicely. Yeah, I mean, this is an interesting prospect, but I have no definitive answer. Yeah.
Okay, thank you.
All right, let's thank our speaker again.